Let's take a look at a problem from the lab assignment, section 4.6. We have a function here, f of x is equal to 1 plus 1 over x plus 6 over x squared plus 1 over x cubed. And they want us to produce a graph of f that reveals important aspects of the curve, estimate intervals of increasing and decreasing, and intervals of concavity. And then they want us to use calculus to find these intervals. So the first thing they ask for here is the derivative. So what we want to do, what we might be interested in doing, is to rewrite this function so that instead of having 1 over x, for example, we have x to the negative first power. And so if we rewrite these things so that we can differentiate it a little bit easier, that might be better for us. So the 6 over x squared will become 6 times x to the negative 2 power, and then the 1 over x cubed becomes a 1 or x to the 1/3 power. And so when we take the derivative of this, a derivative of a constant is 0, so that goes away. The derivative of 1 over x is negative 1 x to the negative 2. Remember that you have to subtract powers. And then we have negative 12. That's 2 times 6, or negative 2 times positive 6. X to the negative 3 power. And then we have a negative 3. And then this is x to the negative 4th power. So we can write that as is, or we can see if we can write it as fractions. But let's write it the way it is so that we can keep in mind what we need to do, and maybe we might need to take the derivative of again. So we have negative x to the negative 2 minus 12x to the negative 3 minus 3x to the negative 4, and let's check it. Okay, looks good so far. Now what we want to do is we want to set this equal to 0, because that's going to give us our places where, or our critical values. And the way to think about doing this is that each of these has a negative 4, or we can think about factoring out an x to the negative 4. And when we do that, looks like they factor out a negative x to the negative 4, or negative 1 over x to the 4th. And to think about doing that, we're going to take away the negative signs, so each of these things will become positive. And then think about multiplying each of these things by x to the 4th, because we're taking out an x to the negative 4th. And so we're going to get an x squared for the first term. Here we're going to get x to the negative 3 times x to the 4th will just be x to the first power. And then here is x to the negative 4th times x to the 4th is x to the 0, which is 1. And so we have this thing. Since 1 over x to the 4th is never equal to 0, we want to find out when f prime is equal to 0, so that just leaves whatever's inside of the parentheses, the leftover, to be equal to 0. So it looks like we're going to try to factor this, but I don't know if it's easily factorable. So let's see. Let's write this down again. That's x squared plus 12x plus 3 equal to 0. And so according to your quadratic formula, x is going to equal to, it's going to be a fraction. So x is going to equal to negative b, that's 12, plus or minus the square root of b squared, so that's 12 squared, minus 4 times a times c divided by 2a. So let's see if we can simplify. I suppose we can write this down. Well, we have to identify the larger and smaller values. So there's a plus and a minus. I'm assuming the smaller value is the one with a minus. and then the larger value is the one with a plus. So let's see if we can work this out and simplify it a little bit. Because definitely this thing under a square root can be simplified. So we have 4 times 3 is 12. 144 minus 12 is 138. And this is just 12, or this is just 2. So let's double check that. 144 minus 12, 132. It's a good thing that was double checked. In any case, let's see if we can at least factor out a 2 or something, or a 4. It looks like this might be divisible by 4. So let's divide this by 4. And the reason I'm doing that is to see if I can factor out a 2 out of the square root. So 132, let's see. 132 is 4 times 33. This is a 4. And then out of the square root, this is going to be a 2 root 33. And then we can cancel the 12 and the 2 root 33. So the 4 comes out as a 2. And then we can distribute this 2. So this would be, instead of 12 over 2, we can think about it that as -6. And then we have a plus or minus. And then the 2's would cancel here for the second one, and we just have a square root of 33. So I would go 6. It looks like they are looking for an exact value here. I don't know if you can put decimals here, but we'll put the exact value. So that was -6 minus root 33, and then we have -6 plus the square root of 33. Now that we know the critical points, we can check where the things are going to be positive and negative. So we first note that the first factor of our first derivative is always going to be negative. We have x to the fourth, which is positive. The reciprocal is positive, and then you have a negative sign outside. So this is going to always be negative. And so now we're just really going to be concerned about the sign of this factor, x squared plus 12x plus 3. All right, so they want us to figure out what happens from -infinity to this point. So 33 is, square root of 33 is probably a number between 5, square root of 25, and then 6, square root of 36. So this will probably be pretty close to 5 point something, 5.7-ish. In fact, we should probably look it up real quick and take a guess. So that would be 6 with a minus sign. Oops, let's try that again. -6, and then a minus a square root of 33. So square root of 33. Oops. Let's try that again. Second function. Alright, let's check it in the calculator. We have -6 minus the square root of 33. That's -11. So if we want a number to the left of that, we want to probably choose -12 or something like that. So we'll choose -12. And if we choose -12 and we put that into this factor, the quadratic, we're going to get positive 144 plus, this is 12 times -12, that's -144 plus 3. So this is going to be a positive. But remember that this was a negative, so it's a negative times a positive, and that'll give us a negative, which means our graph is going to be, the graph of the original function would be decreasing. Now we need to pick another number between like -6 minus So this is about negative 11, and if we have negative 6 plus 33, we get a number like negative 2.55. So I don't know, negative 6 might be a good one. Negative 6 squared is 36. This is going to be negative 72, so this is going to be negative 36 plus 3. It's going to be a negative number overall, but then you're multiplying by another negative, so this is going to be a positive. So that means our graph is going to be increasing. And then we want to pick a number that's bigger than this. It looks like a 0 plays a factor in here because that's where this is undefined, so that's another critical point. So if we pick a number between this and 0, that's going to be really tight. But maybe negative 0.1 or something like that. We can just put it in the calculator, I suppose. So a number between negative 0.255 and 0 would be negative 0.1. So let's try negative 0.1. And then we'll square it according to this. And then we're going to multiply or add 12 times that same number. So let's put a parentheses here, negative 0.1. And then we add a 3. So this is going to be a positive number, and this is going to be negative. Remember that this expression gets factored in. So a positive number from the quadratic and a negative number from this will give us a negative number, and it's going to be decreasing then. And then when we pick any positive number here, this is going to be positive because everything's positive, and then we multiply by another negative number. So the derivative is going to be negative, and so the original function would be decreasing. All right, so we figured out when things are increasing and decreasing. So now let's go back over here and take a look at something happened here. Let's take a look at the second derivative. So this is our first derivative. The second derivative would be taking the derivative of this, bring the negative 2 down, it would become a positive 2. Positive 2 down here, and then subtract 1 from the power. This will be negative 3. This will be a positive 36, negative 4, and then this will be a positive 12, negative 5. So we can just put it exactly as is. We have 2 times x to the negative 3 plus 36 times x to the negative 4 plus 12 times x to the negative 5. And we're going to want to know when this is equal to 0 to find our potential inflection points. And so we do the same trick over here. We take out or factor out an x to the negative 5. And it looks like they're all factors of 2, so we can take out a 2 also. And here, if we can factor this quadratic, that would be great, but it looks like one of those quadratics that you can't factor again. So let's see if we can factor this or use a quadratic formula. So we have, I think we might need to go to the next page here. We have x squared plus 18 plus 6. Oops. Let's make this into that. This is equal to 0. And so the quadratic, I'm going to use this as a template for my quadratic formula. This is b negative 18. Oh, this is negative 18x. Negative 18 plus or minus 18 squared. I think I'm going to need some help here. 18 squared. That's 324. So 324, 4a, and then c in this case is 6, and then 2a. All right, so what is this equal to? Let's go ahead and punch this into our calculator. 324 minus 24. Well, that's 300, I think. Square root of 300. Does that have a 4 in it? Let's see. 300 divided by 4. That's 75. So we can take out a 4 again with the same trick that we did over here, where we took out a factor of 4. So if we take out a factor of 4 inside of the square root, that comes out as a 2, and that would make this a 75. And then we can just take each of them out. We have 18 divided by 2 is 9. That's a negative 9, plus or minus, and then the square root of 75, because you can cancel the 2's. So that looks like our values. Minus 9. The smaller value would probably be the one with a negative. And then minus 9 plus square root of 75. All right. Now that we have the possible inflection points, by the way, 0 is also another possible inflection point, so we want to consider that. So now that we have those possible inflection points, what we're going to do is check around them. And the way they have this set up, it looks like these two will have the same signs for minus infinity to this point, and then this point to 0. And then whereas between those two possible inflection points is another area, and from 0 to positive infinity, where everything's positive, is going to be another the same signs according to them. We probably would have to make sure we draw a number line and check, but in this case they gave us a pretty big hint. So if we let's do this one first, because it looks like it's going to be 0 to infinity, so that just means it's positive. So we're looking at the second derivative and putting a positive number in there. 2 divided by x to the 5th would be positive, and then this whole thing, since they're all positive, will still be positive. So I think it's pretty clear that this is going to be a positive, which means it's going to be concave up. So now, if we're trying to find a value that's less than this point, negative 9 minus 75, I probably would like to know what that is approximately. We can approximate, but we can also have a calculator, so let's just put it in. We have negative 9, and then a minus is the square root of 75. So negative 17, you want to go a little bit to the left of that. Maybe negative 18 is a nice number to choose. So let's put in negative 18 into the quadratic. So let's put a parentheses and say negative 18, and then we'll square that. And then we have a plus 18 times negative 18. So that's like the 18 squared. That's going to cancel itself out, and then we have a plus 6. So this is going to be a positive. Now we're putting a number that's a negative here, negative 18, and x to the 5th is going to produce a negative number. So we have a negative here and a positive here, so that's going to give us a negative value. And it looks like it's going to be the same if we choose a number between negative 9 plus root 75 and 0. So because that's a negative, our concavity for the original function is going down, and we'll go ahead and submit that. Okay, it's probably going to be good for us to take a look at the graph. I tried graphing it on a graphing calculator here. our function 1 plus 1 over x plus 6 over x squared plus 1 over x cubed, and I get this. So it's really hard to find those values where you have especially the maximums and minimums and stuff. And so I have another program called the graphing calculator. This is a graphing calculator on a computer. And let's take a look at the graph of this function. Again, this function was 1 plus 1 over x plus 6 over x squared plus 1 over x cubed. And pretty much the same picture that we saw. We have a vertical asymptote at 0, so that wouldn't qualify as an inflection point because it's undefined there, or a maximum or a minimum point. It looks like there's a little maximum that happens up here when x is equal to -2. We saw that earlier as a change in direction. When x is positive, it just keeps going down, concave up, so there's nothing to really see there. The difficult one, I think, that's tough to see is this maximum or minimum point that happens here around. If we take a look at it, it goes from negative, or it goes from negative going down to positive going up, and that happens at -6 minus square root of 33, which is around negative 11.75-ish. So it's hard to see this. If we zoom out, the reason I like this program is it allows me to quickly zoom in and zoom out. If we quickly zoom out, it's hard to see. If we zoom in, it's hard to see. And so what I'm going to do is I'm going to see if I can compress this a little bit. I'll compress it in the X, and then I'll extend it or make it wider in the Y. So I'm stretching out the Y-axis. And if I stretch out the Y-axis enough, you'll see the exaggerated view where you have the minimum value happening at -11 point. I guess here it's 68 now, and so that's the value of the minimum. Anyways, that was just interesting to look at. Again, the value of the maximum happens. Let's go up to the top again. It's hard to see. It's around -0.2, I think. Let's zoom back out and then see that this is happening all the way up here. And if we again do the proper zooming in or zooming out, we can see that maximum value happening. All right, so that's just a nice view of the graph. Although you're not expected to graph it, just because it's really hard to do this on a graphing calculator to find the appropriate zooming in and zooming out. I decided to use this function or this particular program to take a look. Okay, hope that helps.